All right, without further ado, our next presenter is Dr. Soheil Nazarian. He's the professor of civil engineering at the University of Texas at El Paso. He's the director of Center for Transportation Infrastructure Systems at UTEP. And he's the associate director of Southern Plains Transportation Center. Help me welcome Dr. Nazarian.
Good afternoon, and it's a great pleasure to be here, with our partners at OU and OSU, and any other, and Langston, of course, yeah. And it's always a pleasure to come here and enjoy the hospitality of our friends from Oklahoma. Okay. My talk is a little bit general. It's not very, very specific, just basically it's after lunch. You don't want heavy equations and things like that. So my tone will put you to sleep. You don't need to have the slides to do that too. Just want to talk a little bit about quality management. And the secretary mentioned that they want to extend the life 1.5 years. That's not very ambitious, but it's very realistic. Maybe some of that 5%, we can get it by doing a better job of quality management in general. So that's the theme that I'm just talking about. I avoided quality control, quality assurance, because those are good for contractual. Quality management is the overall picture that everybody would be involved into the system. So this is the outline I'm going to go through. What is basically the quality management? Where are we now? Where we would like to be? Some of the tools, very briefly, and what are the technical barriers to get there? And more importantly, what are the institutional barriers? Because in our business, they don't teach you in the university, right, how to deal with the politics of it, But that's one of the joys of our job, that we have to consider that. Okay, so with the cartoon, I'm going to talk about bases because I'm a geotechnical engineer, but I'm going to refer to the other materials too. Bases is a reasonable value-added material, and we're going to put it. Okay, so what do we do right now? There is a designer sitting in an office, at least in Texas, I know, at least 10 miles away from everybody else. They put the designers in a separate building, and dreams up that he wants to design a pavement with a modulus of, let's say, 60 KSI. Doesn't matter. Okay. And then he conveys that to the laboratory. The laboratory comes up with a material that is essentially durable and constructible. We are looking at the moisture density curve, and you look at the gradation, right? Nothing to do with what the designer do. And then we go to the field, and what do? The inspector is looking at the density. So there are basically no communication between these three guys. Everybody does their job to the perfection, but they are not related to performance directly. So what I would like to do, I would like to take it to a place that the designer would assume that's 60 KSI. And then when it goes to the lab manager would say that, okay, this is a material with 60 BSI, or laugh in the face of the designer. What do you want? What? Okay. And then what you would like to do is just like the inspector to make sure that you got that 60 KSI. I'm using a base, but it's not unique to the base. Look at the concrete. What are we looking at? A specimen that we put it in a top of water for 28 days, and we are paying based on that. After the concrete is poured, nobody cares about how good the finishing is. Nobody cares about how you cured it. Same thing with the asphalt, all of them. We have this one that a lot of other industries, they do not have. So when we say the big picture for the quality management, so the first thing we want to do, we want to just let the people who are in charge of the construction quality and the design process and material selection, they talk to each other in a coherent manner, give feedback to each other, and then to make sure that we get the performance. Performance, now you define what performance you want it to be. Whatever it is you're achieving, and with a certain amount of risk. We know that you are not ceramics that is $500 an ounce, you know. There's some variability, so whenever there's a variability, there is a risk. There is a risk to the owner, there is a risk to the contractor, both of them. So the final goal is to have a payment to last, for instance, to the predefined number of load application. So in order to do that, the first thing we have to do, we have to settle on a design, for the better or for the worse, you know, wherever we are right now. This is what we're going to follow to define the performance. Define the parameters that are important, and then focus on those parameters throughout, you know. So basically, you're involving the pavement engineers, lab engineers, and construction engineers, and the contractor. Everybody's working through the same goal. There are some risks, huh? So we need to manage this risk. Okay, well, the agency, the DOT, you know, it deserves a high quality material pavement that they're paying for it. At the same time, the contractor deserves a reasonable profit. So we have to share these two. So basically, we're trying to minimize the rehabilitation and maintenance, prolong the thing. Now, there are a lot of things that impacts it. The main important thing is the type of contract in the risk management. When you have design, build, maintain, the contractor has to pay a lot of attention because they own that piece of property for 50 years. Okay, so you better initially build it correctly so that you don't have to spend a lot of money. But when we go to traditional design build, bid build, the moment that you put the density gauge down and you say good, you own it. So now the owner agency has a risk. And the worst one of all, and I've seen a few of them, is the design build. You give the contractor the freedom of designing and build it, but not to maintain it. Okay. And then the importance of the layer, you know, if you are just putting a seal coat on the top of the base, do you really want to do the same amount of quality control when you bury that base under 10 inches of asphalt? Right now, all the specification, we do the same thing. And the other thing is, I don't know how to bring it in, but it's legalese. I'm not a lawyer. You know, the performance. There are some contractors that are good. There are some contractors that are very good. We don't have bad contractors, but you know what I'm saying. There's a different level of goodness. And somehow that if we can bring it to the equation, we can look at how often to do the inspection and so on and so forth. So I just basically demonstration of the process. We have a 3-layer pavement, not common, asphalt, a base, and a subgrade. We're trying to build from the base down. If you look at the structural impact, as the thickness and the type of materials that you're using, one layer and the other one becomes predominant. If you have a thin layer of asphalt, the base is predominant. If you have a thick layer of asphalt, the asphalt is important. And one of the things that we have done, we are coming with a structural impact chart. There are basically 2 thicknesses and 3 modular. Which one of these 5 are the most important over here? In this case, you know, the modulus of the base and the modulus of the subgrade is controlling because it's been a thin roller road, for instance. Okay. Now, when you define what material, you can define what parameter of it. You know, we have constitutive model. We understand how these work, you know. We know that the density and moisture is important, but there are a lot of other parameters that comes in. So you can focus on that. So for the pre-construction, you know, first you identify and make sure the design is appropriate, and then based on the importance of this and the variability that we know devices have and the natural variability a conscientious contractor would have. You know, there's no way they can make it perfect. We can come up with a sampling not a piece of paper that says that this is minimum sample. For this project, this is the sampling that you require. And this is the one that we have done for Texas Department of Transportation. Basically, it tells you how to sample and which one to sample. Why do we do this? Because if you go even to the bridge side, when they're building the bridge side, so somebody is pouring concrete on the bridge, and there is earthwork right next to it, right? If you look at it, there are 6 inspectors looking at the concrete, while the embankment, they are putting in 3 feet layers of soils and then bless it by going once over it and keep building it. There's no inspector over there. It may show up twice a day, just doing one sample. Okay, and then we spend millions and millions of dollars to get rid of that bump at the end of the bridge. So if you take 2 of those 6 inspectors of the concrete, put them on the earthwork, I guarantee you the concrete would not suffer, but you're going to have a better quality road. Amen. Thank you. Okay. So, and then during construction, we are advocating a dynamic quality control. If everything is uniform and according to specifications, and the contractor shows that he can give the uniform product, well, by all means, reward him by less testing. If they cannot have a processing control, they keep increasing the number of samples. It reaches a point that is not beneficial. They need to stop the work and figure out how to bring it to the control. Okay, that's what we're doing. So basically, we are doing is trying to find a balance between the importance of the project. We don't want as much emphasis on a secondary road than an Interstate 40 over here, going through the town. Laboratory testing, field testing, and analytical model. We have to balance these. You cannot have one being more perfect than the other one. Some of the new tools, and not so new tools, but they're still new tools because very few DOTs have adopted it. Deflection-based methods and seismic-based methods. These are the ones that elusive replacement for the nuclear density gauge. Everybody talks about it, and so far the only one who has done it really is Indiana DOT. Indiana DOT doesn't have a nuclear density gauge. So they went all the way out to do it. What are these? The deflection methods. Basically, you drop a weight on top of the material when its compaction is over, like a dynamic plate load test. And basically, you assume that the pavement system is one layer, and you get a modulus. So now we are getting a modulus instead of getting a density or moisture content. We say that moisture and density definitely impacts the modulus, but you design for modulus. Why don't you measure the modulus? Seismic methods, just basically based on the wave propagation, and you just basically try to find how fast the waves propagate between the sensors, and this is a source. And based on that, you can get a modulus. The good thing about seismic is that you can get the layer-specific information, and you have laboratory testing that you don't need a transfer function. The deflection methods is good. It's just that you get the system, so you cannot delineate based from the subgrade or so on and so forth. Intelligent compaction, I guess I'm out of line over here with OU being one of the gurus of the intelligent compaction. It's an extremely good process control. You just know how much variability you have, and so on and so forth. That's another thing to consider. And basically, I'm not going to dwell on this one. The component of the IC is basically you have a GPS unit and a sensor and a roller that you measure the stiffness almost continuously as you drive for every pass. Sometimes we say that it gives too much information, so right now data management is a big issue. But other than that, basically you cover every inch of the material. I would like you to, some of these things that I was talking to you, just show you to an example. So this is a site in Dublin, Texas, the home of the best chicken fried steak in the state of Texas. There is one restaurant and there are two items on the menu, either the chicken fried steak or fried chicken. Leave on that on 7 days, you know. Okay. And basically, we took a 450 feet or so of a project, and we divided it into 3 pieces. We intentionally putting one at the optimum moisture content, that's what everybody wants. One of them we made it dry a couple of percent, and another one we made it wet a couple of percent. This is the tolerances that we give, right? They said that the optimum moisture content plus minus 2% or 20% or whatever, you know, in that range. We just to see what's going to happen. And if you look at over there, there are 450 feet. We have around 45 data points that we did everything. You know, it's crowded. You see, this is the LWD lightweight deflectometer, seismic, NDG, a couple of other equipment that I'm not going to discuss over here to cover it. Okay, so this is we use the intelligent compaction to compact all 3 of them, so we have the record of what is happening. So this is the sensor over there measuring. We usually show the data like this, you know, the different CMV is the value that we use, the stiffness, the bigger, the larger, the better, or the stiffer the system, and when we map it, it's a little bit, this is pretty, but you know, we don't know what to do with it, you know. Well, so we just look at the distribution from, you know, the distribution of that value, and then we take it one step further to the cumulative distribution to look at it. That's more engineering than those pictures. And I love those pictures, but we cannot do engineering with it. So, impact of the moisture content. Over here, you see that we have dry of optimum. And basically, what you see over there, the red one is the 3rd pass, the yellow one is the 6th pass, and the green one is the 9th pass. And you see that gradually we are getting better, so it took 9 passes to get to all the points passing the density. Our goal is to pass density. So every point that I show you pass density. Okay. Now, if I put it at the optimum, you see that this is, again, the 3rd pass, and yellow and green on top of that. You see that it's more efficient. As a contractor, you know, I saved 3 passes. By 6 passes, I got what I got with it when I put it dry with 9 passes, pretty much. And then we go and look at it when I'm putting it wet. Okay, the red one, you remember that was the 3 passes, and the black one is 11 passes. We don't have any black. And I'm going the other way. I'm just basically shoving the material back and forth, you know, just making all of them pass density. So this shows the impact of the moisture content. Again, every single one of them would pass. You would pay. You would buy every single one of these three data points. You know. Okay. So the other thing is the definition of the quality. Okay, we want to buy 1 layer at a time, right? We don't want to buy the whole system. So when you have a roller over there, you're just basically vibrating 6-7 feet of the soil. Okay, so you're buying the whole system. So we want to buy 12 inches at a time. So one thing that we have started looking at this is the existing subgrade. We map it, and then we come and map it again with a 12-inch lift. So we say, contractor, go ahead and give us another 12 inches of embankment. And this is now what happened. So if I want to buy these two, one way of looking at it is to subtract these two from each other, right? This was the stiffness before, this was the stiffness after. And we are not very ambitious. All we want to get the same quality as the layer below as you go along. So this shows you dry of OMC, you know, after the number of passes. You see that now the distribution of the mapping is before I put the 12 inches, and then past 9 is, or past 11 is the last pass that we collected. You see that well? I get what I had below, now I'm getting it as well. When I put it at the optimum, I'm getting a slightly better a better material. And when I'm putting wet, I guess as I showed you, I'm going the opposite direction. When you look at one lesson number one is that whatever you start as the first layer, you keep propagating up. So if you spend a couple of hours and make the first layer uniform and stiff, the rest of the pavement will build itself with much less effort. So some of the specifications we have, okay, whatever I have, I'm just gonna build from then on. Maybe we need to reevaluate, just if you build the first layer properly, the rest of it, you have put less effort and you get the quality and you get uniform. That's something that may be more effort for the contractors, but at the end, you'll be amazed if you go to the design, build, maintain, you see how many of them they are spending hours and hours and hours on the first layer. They figure it out. And the other one, you say that the moisture matters. Yeah, you have to consider it. Now, we want a uniform material, and you see this shows you the distribution of the moisture content. You know that the specification in text allows plus minus 2%. Well, this is slightly more than plus minus 2%. Now, the density, all of them pass, but you see that, there are somewhere between 108 and 116. So, are you surprised that you have the modulus that changes between 12 and 30? This is the heartburn of a lot of people that they are using the modulus space specification. It varies too much. Of course it varies too much because the other parameters are varying as well. So some of the technical issues that we are working right now is what modulus should be used, what target modulus. You know that with density we know, okay, we know run Proctor and arbitrarily get a density and we said, okay, I want that in the field. We went back and we never figured out why 25 drops from 18 inches is the golden number that you have to get, and now in here, we can do it from laboratory testing, and then how to prepare and what state, and then the other one you can do the field, the test strip. The test strip is time consuming, and so that's an issue that, we are working on it. One way we did it is just that, okay, map what a layer you have, finish the next layer, map it, subtract it. If it's equal, you are good to go. I want to show you over here, this is the moisture density curve over there, maximum dry density, optimal moisture content. And this is the same specimens we are measuring the moduli, the red one. Okay. Oh, I thought that I had the punchline written over here anyway. So if you look at it, if I go plus minus 2%, I would get around 6% difference in the density. I get 300% difference in the modulus. So that's why you have a much bigger impact in the modulus than you have on the density. The other issue is the drying. As the specimen gets drier, the modulus goes up. And as soon as it starts soaking, it's just going to go down. But let's focus on this one. If I'm a contractor and I'm doing a modular space, all I have to do, I have to wait to let the modulus, let the material dry. So institutionally, we have to control how many hours or days after the compaction you have to accept it. With the density, you can go dry density. You can finish it on Friday and test it on Tuesday. Doesn't matter. With the modulus, most probably, if you finish it on Friday and wait till Friday, Tuesday is gonna pass, especially in the hot climates that we are. Yeah. This shows the effect of section 1 and section 2 are the same one. This is 7 days old. This is 1 day old. You can see the difference in the modulus because of the drying of the specimen. So these are some of the institutions. Variability, again, I don't want to keep you over there. You see 2.5%, 6% in dry density, 300% change in modulus. In some of the institutional manpower.
How do you interpret this?
What's that?
I mean, you're saying that the payment is same, but modulus, because you're waiting, changes.
Because it dries, that's how we make brick, right, in the extreme. how do we make the brick? We make a really, really wet mud, and then we just put it in the oven. In the
So
old.
basically what you're saying is that you should test within 24 hours.
Yeah,
48 hours.
usually that's not a problem because the contractor is anxious to put the other layer. You know, if you're accepting, you know, they cannot put the next layer until you accept the layer. So the contractors do not like to wait, but you know, that's what I'm saying, that's hypothetical.
I'm just trying to understand how to parse and make a decision on.
Oh, okay. Again, you control it that, you know, okay, within so many hours or within so much moisture, you have to do it, you know. We just finished the NCHRP project, by the way, on this one. So we have a national specification coming up dealing with this issue. Okay. So the manpower is always the issue, you know, we are trying to do more and more with less and less, you know, less and less inspector. But, you know, if you are trying to save 5%, you know, why don't we just shoot for 8% and take 3% of that and just put it into the quality control, huh? We achieve that 5% by spending a little bit more. Budget limitation, you know. And look at it, in aerospace, we spend 85% of the budget is the quality control. We spend less than 2% of our construction budget on quality control. Can we increase it by a couple of percent? It's still within the noise, right? You know, it's a small change order to get more. How much, I mean, we have to look at the cost benefit that you have when you have you don't have premature rehabilitation or you don't have unintentional reconstruction because of the variability that we have. If you minimize potholes, you know, if the whole thing goes away at the same time, you save a lot of money. And then to get the buyout of everybody, you know, AGC has to buy it out, the DOT has to buy it out, and the technical community, ASTM, and things like that. So we need a partnership amongst all that is to see the benefit of this new technology and thinking a little bit more long term than, you know, hey, what's going to happen to my profit to the next project or what's going to, things like that. And that is happening. So I just leave you with this one. It's almost, this is a 10-65, that's the NCHRP project. You're talking about the risk and buyers and sellers. And you see that these are the sensitivities. Seismic 86%, 64%, and 44% for density. So density is not a good indication of the quality. This is independent work. No? These are intentional defects that the ARA was a contractor. They asked the contractor to intentionally screw up the construction. And the density only found 44% of it. But if you look at the variability is high too in the modulus, much higher than it is in the density. So automatically we start blaming the equipment. No, it's not the equipment. It's the way we build it and the material. So we have to consider that. Anyway, I just don't take too much time over here. I know I've gone over. Just basically, this is a concept. You know, there are a lot of challenges, but it's by far better than what we are doing right now in terms of getting a more uniform and getting a higher quality. There is a growing pain, but the contractors and the owners, they need to share this pain to get there. I would like to thank you and appreciate the invitation and invite everybody come to our campus. We are the miners. This is the new 100-year peak. If you haven't seen it, you know, this is a miner peak on campus. I apologize if I went over. Thank you.